Hello, good evening, class. This is class third, assignment number second of quantum Hall effect. TA. This is a course offered by NPTEL 2025 August. So, in today's class, I will be discussing few of the problems and the solution of those problems, how to approach these kind of questions in exam. Apart from that, the few of the fundamental concepts about the Landau levels being okay. So I'll just see the sheet. Okay, I'll be discussing about the incompressibility of the quantum Hall states, the degeneracy of those states, and the density of state accompanied with these quantum Hall system. Then I'll be discussing the conductance formula for this 1D channel, and in the last part, last part of it, I'll be discussing the Corbino geometry, how it can measure the transfer of a charge, basically the quantum pump, and at later maybe we'll discuss the potential profile of this quantum Hall system. Okay, having said that, I will start with the first question. Question number one, which says that show that the quantum Hall states are incompressible. Show that quantum Hall states are incompressible, means you can't compress them. Okay, so first we'll have to understand what does the compressibility mean. What does the compressibility mean? So we know that in the class also the professor has discussed the compressibility part. I will just take the thermodynamic definition of it. So a state is thermodynamically okay. So let me just first define the compressibility. So compressibility is defined as parameter kappa, and that will be 1 by n square, and is the number density del n by del mu at a constant temperature. This has been derived in from class notes. So what does the compressibility mean? It actually means like how many like number of the carriers you can put it in a system when you change the chemical potential by delta mu. It is essentially related to that, like how many available number of states are there in which you can put the carriers if you change your chemical potential by delta mu. So if the question is saying that show that quantum Hall states are incompressible, incompressible mean your kappa, basically the compressibility is zero. You can't compress the system. You can't put any carrier if you change the chemical potential. Those states are not available. That's what it essentially means. And in our case, I'll just write it down, whatever I'm saying. state is thermodynamically incompressible when the compressibility when the electronic compressibility if you see this del n by del mu is essentially dense state. Basically, when a dense state is goes to zero, you don't have any available states in the system. Relative compressibility kappa vanishes or is very very small or is very small. Equivalently, the density state does not change when the chemical potential mu is varied within an energy gap. So the density does not change when the chemical potential mu is varied. Mu is varied within an energy gap. That is essentially del n by del mu equal to 0. This implies kappa is equals to 0. Now we'll see what the profile of your del n by del mu in case of the quantum hole. If it is 0, like then we'll say that okay, the kappa is essentially 0. So we know that. So I'll write the argument for integer Hall effect. Argument for integer quantum Hall effect. In a large perpendicular magnetic field, we know that the energy states goes like this. We have discussed in the previous class: h bar omega c, n plus half, where n is your quantum number, which can take integer values, belongs to z, and basically this n is 0 means the first Landau level, 1 means the second Landau level, and that's what it means. Where omega c is cyclotron frequency, c, which is Eb by m. Okay. So now if I draw the profile, you have your energy on this axis, and then you have n is equals to 0, n is equals to 1, n is equals to 2, n is equal to 3, and the spacing between each of these is h bar omega c. Okay, right? So now if you are at integer n, for example, say let's say you are sitting at n is equals to 1, and this Landau level is completely filled. So if you change the chemical potential by, for example, if you move your chemical potential mu here, in that case also there is no available state. Your number of the carriers is not changing because the number of the available states are not there. So even for finite delta mu, delta n is essentially 0. What this implies? This implies that delta n by delta mu is 0, and this tells your kappa goes to 0. So it means quantum Hall states are incompressible. That's what it means. Remember, these are the Landau levels. Point note is that these Landau levels are of bulk and incompressible. So the edge of the sample host gapless chiral modes. what we call the edge states, and they carry current. So this incompressibility statement, it refers to the bulk. Okay, so this was the first question in which we discussed that, okay, the quantum Hall states are incompressible. We define the compressibility kappa, which is 1 by n square del n by del mu at a constant temperature. And then we looked for the profile of carrier density versus the chemical potential for the Landau levels in this part, that even if you change your mu, your n is not changing because available states are not there. Okay, so let me just, for the notation, let me just keep it capital N so that you don't mess up it with the small n. So here you are. So small n is your dense, your basically carrier density, and the capital N is your Landau index. This is capital. Yeah. So this is the question number first. Now I will come to the question number second, which I will discuss now. And the question number second goes like, density of states of the Landau level. If I ask you, what is the density of state profile of the Landau level? We know that for the two-dimensional electron gas, where dispersion is x bar square kx square by 2m plus x bar square ky square by 2m, for that the density of state is constant. Then this is the basic condensed matter. So, but if you put the same electron, two-dimensional electron gas in a perpendicular magnetic field, and it forms these Landau levels, which we have discussed in the previous class, how the density of state of this system then changes from the normal two-dimensional electron gas in zero magnetic field. So the question goes like, compute the density of states of Landau level. So we know that each Landau level has, so, okay, so let's say the degeneracy of the Landau level, this is, we have discussed degeneracy of the Landau level, each Landau level. How it's defined? It is essentially phi by phi naught, right? G is phi by phi naught. Phi is the flux threading through your sample, and phi naught is flux quanta. So if I ask you what is the degeneracy per unit area, see, per unit area, let's say, let's define it by n phi, that will be G by A, and that will be equal to B by phi naught, right? And phi naught I can write H by E, EB by H. Remember, H by EB is, H bar by EB is nothing but, okay, I can write it like EB by H bar into 2 pi. H bar by EB is magnetic length square, right? So you can write n phi as E by 2 pi times 1 by LB square, where LB is under root H bar by EB. This is the magnetic length. This is basically the separation between, this is the spread of the your Gaussian of the your Landau levels, basically the magnetic length. And these Landau levels, if I draw the picture, what you will see is like, this is what the profile of your Landau level spectrum is, right? This is n is equals to 1, 0, n is equals to 1, n is equals to 2, and then so on, it goes on. So y-axis is E, right? And so the only available states are when these Landau levels are there, other states are not allowed. In that case, it will be Dirac delta function, right? So I will write, so the levels are delta functions at energies En. So density of state per unit area, GE will be N phi, that is your degeneracy per unit area, that is the degeneracy of each of the Landau level. Then N goes from 0 to infinity because there will be infinite Landau levels. You put in the magnetic field, and E minus En, where E is your energy or the energy at which you are sitting, and En is essentially the energy of your Landau level. So En I will write as h bar omega c n plus half. So this is your essentially the density of state per unit area for your Landau levels, and it is a Dirac delta function. And if you, this is like, remember, this is by not including any kind of disorder, broadening or thermal broadening. If you have to include those, then your Dirac delta function gets replaced by the Lorentzian or the Gaussian. Yeah. So in this question, we discussed that what is the degeneracy of the Landau levels, density state of the Landau levels. So we initially started with the degeneracy of the Landau levels, then we degeneracy per unit area we calculated. It turns out to be E by 2 pi LB square. We know that the energy spectrum is versus E versus N is like it's discrete and it's a Dirac delta function type. So we take sum over all the Landau levels 0 to infinity. Dirac delta function. E is the energy of the system. En is energy of the Landau levels, and n phi is the degeneracy of each of the Landau levels, and G is the density of state per unit area. Okay. So this is the question number second. Now I will come on to the question number third. Question number third, which says that for a 2D electron gas in the presence of perpendicular magnetic field B, write down Ohm's law. That is, what is Ohm's law? J is equals to sigma E. If you remember, that is relationship between the electric field E and the resistivity rho. Electric field and resistivity rho. Then express relationship between E, electric field, and resistivity rho as a 2 by 2 matrix. Along with, and the explain your notations also, whatever notation you use, explain those notations also. So having said that, I'll start the solution of this question, of this problem. So we want solution. We want the relation between electric field E and current density J, because J is equals to sigma is the Ohm's law, right? In linear transport, of course. So J is equals to sigma E, and E is equals to resistivity and your current density J. So what does this imply? If you take J is equals to sigma, instead of E you put J, this implies sigma J, and this implies that sigma and rho matrix multiplication will be equals to 1, and this simply tells that your resistivity is essentially inverse of your conductivity. So in 2D system with perpendicular magnetic field, you break the time reversal symmetry and it's isotropic in plane. So the conductivity tensor in that case will take the form in 2 by 2 in two-dimensional system, 2D system. Your sigma, let's say you define it like sigma xx, sigma xy minus sigma xy and sigma yy, and the rho, let's say you call, of course you will define the rho xx, rho xy minus rho xy and rho xx. Let me explain the notations here. So your sigma xx is longitudinal conductivity. This is like, if I write in simple words, it's current response parallel to the applied electric field in the direction of applied electric field. Similarly, sigma xy is, we know that whole conductivity, which is a transverse response to the applied electric field, and rho xx and the rho xy are the longitudinal and whole resistivities respectively. These respectively. And remember what I have written in this equation 1 and equation 2. If you see, these off diagonal term component are negative. This is negative and this is negative. This comes from the fact of the Onsager relation, that the antisymmetric sign reflect Lorentz force, and Ey due to Jx is plus minus Jx. In that case, okay, so this is something which I have discussed in the previous class assignment 1. You can follow why it's negative. And then if I already have sigma xx and sigma xy, I can just take rho as in terms of sigma inverse equals to 1 by, if I ask you that you have a matrix A, which is A1, A2, A3, A4, if I take inverse of it, it will be 1 by A1, A4 square, A1, A4 plus A2, A3, and with an exchange of like A1, A4 and minus A3 A2. So if you follow the same for rho, which is inverse of sigma, this will turn out to be sigma xx square plus sigma xy square and sigma xx minus sigma xy, sigma xy and sigma xx. So components, if I compare, your rho xx is essentially sigma xx by sigma xx square plus sigma xy square, and your rho xy is minus sigma xy by sigma xx square plus sigma xy square. And now this is for the normal. This is general expression of relation between conductivity and resistivity. Now moving on to the next question, which I propose that, okay, show that in the case of the quantum Hall effect, what will be the value of the rho xx and what will be the value of the rho xy. How it will transform for quantum Hall system. How the results of conductivity tensor and resistivity tensor transform for integer quantum Hall. Okay, so this is the question. We'll take this question now. Okay. So I will be explaining a baby version of it, not from the Kubo formula, but a baby version, which will help you get the conductance of in case of edge modes. So we know that the velocity, I'll start by it, of the particle in magnetic field B. So you can choose then its corresponding vector potential is given by vector potential A basically. Mx dot is x dot is essentially velocity, is P plus EA, right? Where Pi is canonical momentum. Current is, how do you define the current? Current is essentially minus E times velocity, right? And which means that in the quantum mechanical picture, the total current is given by, in quantum mechanical picture, the total current will be given by I is equals to minus E by M, and then summation over all the field state of your wave function psi and your then minus your momentum basically mx dot. You write here, this is your canonical part, this is your vector potential part, and the expectation of this value over the psi, and then sum over all the field state. Now it's, if your applied magnetic field is perpendicular in that case you can choose, you are free to choose your vector potential, and it's best to do these kind of calculation in Landau case of A is equals to x b y cap, for B is equals to b z cap. You can choose, you can choose A to be x b y naught, and if you do so, then your Ix will be minus E by m sum over your k, your psi n k, your n is the your Landau level number, then minus I h bar del by del x psi n k, and your n will be 1 to your whatever your filling factor is there. So we introduced an electric field E in the x direction, so the Hamiltonian and these things will go like this, and with the new Landau levels field and the current in the x direction like this, right? And if you see it, what it's essentially doing is psi n k are the wave functions of your harmonic oscillator, and if you compute the expectation value of the momentum of the harmonic oscillator, we know that it goes to 0, right? And that's why your Ix will go to 0. This term basically, this term will go to is expectation value of momentum of harmonic oscillator goes to 0. Okay. How can you understand it? So the way to understand is psi nk will either be uh, even, will be even function, will be even for n is equals to even, and will be odd for n is equals to odd. And your term, let me call this term A will always be odd, therefore A will always be odd. And it's sum over all the k's from minus infinity to plus infinity. If you take minus x to minus k to plus k, if you sum it overall, so it will essentially go to 0. The summation will eventually will go to 0, right? And that's what it means. So your Ix will be 0. This implies your Ix is 0. But meanwhile, we can compute the current in the y direction. Meanwhile, the current in the y direction can be computed. Your I current in the y direction will be essentially the same minus E by m, or Landau number n equal to 1 to filled Landau level of nu. This I h bar del by del y, plus this time it will be having another term which will be E x b and psi n k. You know that why this additional term comes, because of your, this is essentially coming from your uh, Landau case, and if you take it, this will go like Iy is equals to minus E by m, n is equals to 1 to nu. Your first term IH bar del by del y will go to the summation over IH bar del by del y will go to 0, as we discussed for del IH bar del by del x. But your the second term will survive, and it will be psi n k E x your I h bar del y for it will be what h bar k plus ebx and psi n k, because your psi n's are the wave functions in the x direction. So, and the second term, so why it happens, like I will explain just. So if you have your magnetic field, why this is h bar k and not 0? If you have magnetic field applied in the perpendicular direction and you choose your Landau gauge to be bxy cap, in that case your wave function psi, let's say instead of psi, let me call it some phi, will be uh, e to the power I k y x e to the power I k y y and times the harmonic oscillator function of x. It will be like this. Let me just call it maybe some another wave function of let's say zeta n k. It will be like this. So if you are operating IH bar del by del x, then this is the harmonic oscillator function. Harmonic oscillator function. This will make the expectation value momentum to be 0. But if it is IH, if you are taking IH bar del by del y, if you are taking the IH bar del by del y, then the expectation value of your phi minus IH bar del by del y, phi will not be equal to 0 and will be equals to h bar ky. That's why this term h bar k comes here. It's h bar ky essentially. And yeah, so this is just additional information. Having said that, the second term above here, if you see the second term, is computing the position expectation value x of the eigenstate, and we know that the expectation value of x is essentially minus h bar k by eb and minus eb by me by eb square, because it's shifted by that center. And let me just write what I'm saying. So the second term of equation, let me call it equation number 3, equation 3 is computing the position expectation value x of the eigenstate, and we know that these harmonic oscillator states are shifted from the origin, so that your psi and k, x and psi and k is essentially minus h bar k by eb and minus me by eb square. The first of this term will essentially cancel your first term in equation 3, and the only term which will survive is this term. So if you substituting 4 in 3, substituting 4 in 3 gives you Iy is equals to sum over all minus E by M, sum over all nu n is equals to 1 to nu, 0 to nu, and then you have sum over all the k. This equation boils down to me by eb square, and Iy will be essentially E cancels down and cancels down, E by B, and your EV Here you will be having EB also, capital E, that is your electric field, and some or all the K's. Some or all your K's. And let me call this equation as your equation number 5. Now we know that the sum over K just gives the number of the electrons, and sum over K will give the number of electrons, the total number of electrons. And from the degeneracy, we know that it will be equals to nothing but BA by phi naught. So if we divide through the area to get, I can just divide IY by capital A, E nu all over K E by BA. So this IY by A will be current density JY. It will be E nu phi, and I can multiply and divide it by your H by E, and that will give me this phi naught. And if you just see it in terms of E, it is essentially, and you can write it as E0 and your J as 0 E nu E by phi naught, right? And in that case, if you compare equation number your 6, and if you compare it with equation number, the one which we had derived here, let me call A, comparing equation number 6 and A, we know that J is equals to sigma E, right? This gives your sigma matrix sigma xx to be 0 and sigma xy to be minus E nu by phi naught. This implies your rho xx to be 0 and your rho xy to be, this will be positive, and rho xy will be minus phi naught by E nu, and phi naught is nothing but h by E, so minus h by E square times nu, which tells you that your resistivity goes as h by E square times your Landau index nu. Yeah, that's what it means. And this is, we have derived the Landau tensor, this Ohm's law tensor of the conductivity for the quantum Hall effect. What is the conductance? So this is what we have derived. Now in the next question, I'll take a problem which will be based on modeling the potential Vx, which is felt by the charge carriers in the two-dimensional system and the quantum Hall sample basically, and then show that the conductivity of the single Landau level is essentially h by E square. So I will write the question. This is question number 4. So the question says that modeling the potential Vx felt by the charges in 2D quantum Hall system sample via the form, this is given Vx is equals to Vx0 plus del V by del x at x equals to x naught, the Taylor expansion, and x minus x naught, and higher order terms are neglected. With the first term, this is constant, and the second term is essentially the gradient denoting the sharp edges of the sample. And using this, we have to find out the conductivity of a single Landau level. So first, I will discuss about the edge modes, like what kind of the edge modes are there, and then we'll come on to this problem. We will essentially solve it, and we'll determine the conductivity of these states. So I'll start from the very beginning. Solution. So there is something funny happens near the edge of the quantum Hall system, and which can be even seen classically also. So consider particles moving in circle in magnetic field. For a fixed magnetic field, our whole particle motion is in one direction, right? For example, you have this big two-dimensional electron gas in which your carriers are moving, right? And initially they were moving in zero magnetic field. Now you have applied a perpendicular magnetic field. What will happen? Your carriers will start orbiting, right? Like this, like this. So all of these orbits will be of circular and of the same size. So let me just, I don't know, I will be able to copy and then paste. I see. Yeah, so the circle I will just copy. Circle I will just copy, and I'll just keep pasting it here like this. So there will be like these circular orbits in your system sample, right? Because now you applied a magnetic field, there will Lorentz force. This will make these your carriers to go around in circle. Let's say that the magnetic field is such that, and the charge is such that your carriers are moving in direction of anti-clockwise. So all of these will be moving anti-clockwise. Since they are not going from one edge to another, one edge of the sample to another edge, there will be no conduction. So you can think like the bulk is insulator. But there is something funny which happens near the edge. Right? If you see the picture which you have drawn and take it to the edge, near the edge of the sample, you will find that okay, it will be somewhere like this, something like this, right? The picture will be something like this. You extend this picture till the edge, that's something similar you will see, right? Because half of your orbit will be inside and half of orbit here will be outside. But you know very well that carriers can't reside outside the sample boundary. So what will happen? They will bounce off, and what we call the skipping orbits. So I'll just put it on the another edge also, and then I'll explain. So if your carriers were going like this, here also they will go like this. And here also, if they are going like this, inside they will be like this. So what do you see here? On this edge, let's say, let me call this edge number 1 and 2. On edge 1, carriers are moving in positive direction, and on edge 2 in negative direction. And that's why your Ix is 0, because your one of the components of current is going in plus direction, another component is coming in the minus direction. They both add up, equal in magnitude, opposite in direction, and your Ix is 0. That's something which we derived here. If you see, your Ix was 0. That's what the physical picture of this Ix0 mean. Now coming to the okay, then at the edges you see these bouncing. So since carriers are not allowed outside your edge of your sample, what will happen? Whatever you see outside will go away. These won't be there. And now you have these skipping orbits which are not fully circle, right? They are like what you call semicircle. And this is what is known as the skipping orbits. Electron is jumping in the edge, and that's how the conduction is happening. And since they have the chirality on edge 1, they will have to move in only positive direction. On edge 2, they'll have to move in the negative direction. So are they have single directions. These skipping orbits have single direction, and therefore they are called the chiral edges. Called the chiral edges. They are chiral edges because they are moving in only one direction. On one edge, they are only moving in one direction. And the particles have opposite chirality on two edges of the sample. Particle have opposite chirality on the two sides of the sample, two opposite sides of the sample, right? And this ensures that the net current in the absence of the applied electric field vanishes. Now we will show that how this edge mode appear in the quantum theory, and the edge of the sample is modeled with the potential which rises steep in that's shown in the figure. So if I draw the potential, the edge potential, how the edge potential will be there. Inside the sample it will be a constant, and outside, since the particle cannot exist, so it will have to diverge. So your Vx will be of the shape, that's how it will be, right? Near the edge of the sample, it will be diverging, your Vx. And in that case, we have seen that we write the Hamiltonian as 1 by 2m Ex square plus Py plus Ebx square and plus this Vx. This first part is for the bulk, and this Vx is of edge. If we take only the bulk part, we will get the Landau levels, but how the conduction is happening through H, that picture we won't get. So we'll have to take the Vx and its profile to get the answer of the conductance in the system. So in the absence of the potential Vx, that is in the central region, this region, basically from here to here, in the absence of the potential, we know that the wave function are Gaussian of width LB, where LB is the magnetic length, root h bar by EB. And the potential profile also is given, and even if it's not given, we can expand the potential using the Taylor expansion, even if the potential is smooth, and your Vx will go as Vx0 plus del V by del x at x is equals to 0 and x minus x0, and the later term we can just ignore, right? So we are then left with this linear potential, which is exactly what we have seen in our course, and this leads to this drifted velocity. So the drift velocity in the y direction corresponding to this potential will be given as Vy is equals to minus 1 by Eb and del V by del x, right? And we know that each wave function labeled by momentum k sits at a different x position, and that we the x also we know that it's minus k lb square, and this we have solved in the previous class, and has different drift velocity. And has different drift velocity. In particular, the modes at each edge are both chiral, traveling in opposite direction. And if you see the profile of the potential, it is like this, right? So here on this side, this is your basically V, and this is your x. So on this side, del V by del x is positive. That means your Vy is negative. And on this side, your del V by del x is negative. That implies your Vy is positive. And so the current is essentially is flowing in opposite direction on the two edges. This agrees with the classical results of our skipping orbits, whatever we have discussed till now, right? So having a chiral mode now is special. It's rather special. In fact, there is a theorem which says that you can't have charged chiral particles moving along a wire. There has to be a particle which can move in the opposite direction as well. And in the language of the field theory, this follows from what is called as the chiral anomaly. And in the language of the condensed matter physics, we call it with the particles moving on lattice and follows this Nielsen. This follows this Nielsen Ninomiya theorem. You can read about it for detail. Yeah. So the reason that the simple example of a particle in magnetic field avoid these theorems is because the chiral fermions lives on the boundary of the this 2D system, right? Rather than in the 1D wire. And this is a part of a general story. There are, so if it's a 1D wire, the both edges can't flow simultaneously, right? Since we have the 2D, so there is separation between the two edges. One is on the one edge, another is on the another edge of the sample, and that's why it works. And there are physical phenomena which can only take place on this boundary of these systems. And these kind of system where edge conduct and the bulk is insulator are known as the topological insulator. And they are a class of insulator in which your bulk always remains like bulk remains insulator and your edges are conductor. And if you want to go from one edge mode to another edge mode, you will have to basically essentially go through a phase transition in which your bulk will also become conducting, and after that there will be a phase transition, and then you can go to another state. So that's why these topological insulator states of the quantum hole are very robust. Okay, so this is all about what the topological states are there, and but let's focus on the problem. So let's now look at what happens what happens when we fill the available states. Available states. And how do we do it? We do it by introducing chemical potential. Potential. So the states are labeled by y momentum h bar k. H bar k. But as we have seen, this can equally be thought of as a position of the states in the x direction. This means that we have justified the field states like this basically. And if you just take your Iy, the expression of your Iy, what it is minus Evy, right? And if you write your Vy in how it will go, minus E summation over del k by 2 pi on the Brillouin zone, and then Vy of that k. And if you take the equation number, let's say this equation number 7, referring equation 7, so Iy is minus E del k by 2 pi times Vyk is essentially 1 minus 1 by Eb del V by del x, minus 1 by Eb del V by del x. And if you see this equation, this is your equation number 8. Right. Your del k you can write as minus del x by Lv square. This is from equation 8. And if you substitute this here, what you will get is Iy is equals to minus E and by Lv square 2 pi, and B also you will get you will get del V Lb square by h bar by Eb basically. So your Iy is essentially LB. If I write under root h bar by EB, it will be minus E by 2 pi h bar and times delta del V. I think here I have done a slight modification with there. This E won't be there. If this E is not there, then it will be like this, and then it will be E square del V, and then you can write it like minus E. E times del V is essentially your chemical potential, so delta mu by 2 pi by h bar is nothing but it's uh, h, right? And you, this was right, whatever. Yeah, this was right. Here, this will go like E del mu, and then EVH is essentially delta mu. If you substitute this one, your sigma xy is what Iy by Vh, and this you will get to be E square by 2 pi h bar, E square by h. This will be E square by h, and this tells you that this is essentially the conductivity of a single Landau level. Yeah. If this is clear, then we'll move on to the next problem, which is the final problem of this class. So the question says that draw a neat label diagram of the 4-pino disk. Label diagram of 4-pino disk. Discuss how it acts as a quantum pump. And also explain the quantization of the whole plateaus basically. Yeah. So this is essentially the problem from the gauge invariance. So here, instead of taking the carriers moving in a rectangular sample, which we were doing earlier, we'll consider electrons moving in an annulus. So we will be having a sample like this, a bigger disk, and then you have another disk. This is your two-dimensional electron base, and you measure two probe conductivity between this A point and your B point. These are your probes, basically to measure the conductivity in a system sample. and you are threading a flux phi through the by applying a magnetic field, perpendicular magnetic field you apply, and let's say the radius here is kept small r, for example. So here, since this phi is the flux which is threading this hole in your sample, you have this hole in your disk, right? This is the phi. So the nice thing about this geometry is that it provides us with an extra tuning parameter in addition to the background magnetic field. B, which is penetrating the sample, we can thread an additional flux phi through the center of the ring. And inside the ring, this phi is a locally pure gauge, basically. Nonetheless, we know that phi can affect the quantum state of the electrons also, right? So let's first see what this phi has to do with the whole conductivity. Let's first see what this phi has to do with whole conductivity. Suppose that slowly I am increasing the phi from 0 to phi naught. Let's say slowly I am increasing the phi from 0 to phi naught. And phi naught I know that it's 2 pi h bar by E, right? H by E, flux quanta. Here, what does I mean by slowly? Slowly has to be done with, has to do with the time, right? And the time has to be larger than something. So here something is this h bar omega b. So slowly here means that we take time t, which is greater than 1 by h bar omega b, the energy scale of these Landau level system. And what will the consequence of it? This will be inducing an EMF, because the changing flux will induce an EMF, right? From Faraday's law, we know this induces an EMF around the ring. And what will be the EMF? EMF will be the change of this flux with respect to time, the rate of change of flux with time, and this will be minus phi naught by this capital T. And now let's suppose that we can argue that n electrons are transferred from the outer to the inner circle in this time. Let's suppose that we can argue n electrons are transferred from the outer to the inner circle. this time. So what will be the consequence of it? Then I can write the current, right? The radial current. So the radial current can be written as IR is equals to NE by T, and then the rho XY will be essentially your EMF by your current IR radial current. Your EMF you have written as 2 pi h bar by E square times 1 by N, right? And this is the result which we wanted, right? So h by E square times 1 by N. So we can say that if you can increase your flux by each time you change your flux by phi naught, your uh, rho xy will be h by e square times 1 by n, and n is your number of the charge carriers which goes from outer edge to the inner edge, or the vice versa, depending on the polarity of the charge carrier. So you can essentially determine whether one electron has gone from the inner edge to the outer edge or outer edge to the inner edge. And this is something which is great of the Laughlin, that he well thought this experiment, and this has been done also and proven also. So this is the quantization, that the quantization of the resistivity, and it will in the form of h by square times 1 by n. So this is all about this problem. So in today's class we have discussed, I'll just recap today's class. So in the today's class we discussed the quantum Hall states are incompressible. First we discussed that show that the quantum Hall states are incompressible. We defined the compressibility. From the compressibility, then we moved on to the shape of these density state del n by del mu of the quantum Hall system, two-dimensional quantum Hall system, and we observed that del n by del mu is 0 for these systems, because even if you change the chemical potential, the allowed number of the allowed carriers are not there, states are not there. So del n remains 0 even if del mu is finite. In that case, your kappa goes to 0, and that's why these states are called incompressible. Then we move on to the next question, which computes the density state of these Landau levels. We know that for the two-dimensional systems, the density state is finite and it's constant. But if for the two-dimensional electron gas, when it's placed in the magnetic field, its density state per unit area basically boils down to n phi, which is E by 2 pi times L by square, basically EB by H, if you better call it, and the Dirac delta functions of the energy levels. Then in the next questions, we discussed how the resistivity and the conductivity tensor depends on each other. This is what comes from the Ohm's law, and that's the final expression of the tensor component. Now we moved on to the next problem, which says that okay, you have derived the relation between the resistivity and the conductivity tensor. How they will go when the particle is placed in the two-dimensional electron gas in perpendicular magnetic field using the approach of these Landau levels. We discussed it, and what we find is that Ix is 0. The current in the x direction is 0. That's why if the current is 0, then your conductivity is also 0, right? So your sigma xx is 0, and your sigma xy is finite, which we computed to be h by e square by h, basically times nu, and your rho xy as h by e square nu. In the next problem, we discussed how your potential profile, depending on the potential profile, the smooth potential profile is there. We discussed the concept of the skipping orbits from the semi-classical model, and initially from the semi-classical model, we understood okay how the chirality is different and the two edges. Later, using the using the similar potential model, we discussed okay the quantum mechanically this time, that how the edge profile is there, the potential profile is there near the edges, it shoots up, and the direction of the chirality of the carriers on the edges is different. If it's here it's positive, then here it's negative, or vice versa. And using the expression of the drift velocity in the y direction, we computed the current, total current Iy, and knowing the Iy, V EVH, which is the whole potential VH, we computed the sigma xy, that turns out to be E square by h. This is what the conductivity of a single Landau level is. Then in the last question, we labeled, initially first labeled the clean diagram of the Corbino disk. This is the Corbino geometry. And then we discussed on how it acts as a quantum pump. Basically, it pumps out the carrier from the outer edge to the inner edge, or inner edge to the outer edge, depending on the chirality of the magnetic field and the charge carrier also. And this explains the quantization of the whole plateaus also. This we did using this thing, that if you change the flux which is threading through your center by phi naught, in that case h by e, basically your this induces an EMF, and that EMF you have now, and you have this current also, Ne by t, because it is changing in time t. Then you can compute your resistivity, and then your resistivity turns out to be h by e square times 1 by n. And n is the number of the charge carriers which are pumped from one edge to the inner ring of this Corbino to the outer ring, basically, or outer to inner. And this is what the quantization which was supposed to be discussed in this problem. And with this, we complete this class. I will wait for 5 minutes. If you have any question or doubt, class is complete. Next class will be on next Saturday. Next class will be on Saturday. Same 6 p.m. If you have any, I will wait for 5 minutes to take questions. If there are any questions, I'm happy to take those questions, and after that I will just close the session. So if you have any question, doubt, you can ask me in the comment section, or you can ask with the mic also, and I'll be happy to address your questions.